In this short video, we're going to cover some of the basics about using Charles' law for our common gas laws. So Charles' law states that in a sealed but flexible container, as you can see that's going on over here in our balloon that's being bathed in liquid nitrogen, that as temperature of a gas decreases in a sealed but flexible container, volume will also decrease. So if you take a look at the data over here, right, you can see that the temperature in degrees Celsius versus temperature in Kelvin, as this decreases, the volume of the vessel containing that gas will also decrease if it's flexible and doesn't retain its shape or exert an outward pressure, right? And if you also look at this graph figure over here, you can see that as our temperature decreases, our volume also decreases in a direct relationship, right? And so the opposite is true also. As temperature increases, the volume of a vessel containing a gas, that assuming the vessel is flexible, will also increase, right? So we can express this as the volume of an object or the volume of a gas is equal to a K constant, which is technically specific to whichever gas you're talking about, times temperature, right? Or the way we'll see it and use it in class, volume 1 divided by volume 1 divided by temperature 1 equals volume 2 divided by temperature 2. Right? And so again, think about what variables are being held constant in this scenario. So here we're discussing the changes in volume and temperature from initial to perhaps what we're observing. So in this case, we're assuming pressure of the vessel is held constant, and we're also assuming that the number of moles of gas in our flexible container are also held constant. Again, so this means that for an ideal gas, under ideal conditions, volume and temperature are directly proportional to each other, right? V1 over T1 equals V2 over T2. Okay, so now let's set up our problem here. Practice problem, right? So I'm going to click this, and there we go. Okay, so we're going to be using Charles' law, right? V1 over T1 equals V2 over T2. So for this problem, we have a sealed flexible container where a sample of argon takes up 0.8 liters of space, is held at 30 degrees Celsius, and is exerting a pressure of 760 torr. So 760 torr should look pretty familiar to you, right? That's going to be the same as 760 millimeters of mercury, or 1 atmosphere, right? The pressure, the amount of pressure that the atmosphere above us pushes down on us with at sea level, right? And so we want to know what the volume of this container and gas will be if this sample occupies, what the volume this sample occupies at 85 degrees Celsius and 760 torr. So the first thing we need to do is identify our variables, right? V1 is 0.8 liters, T1 is 30 degrees Celsius, and remember, for using these common gas laws, you have to convert Celsius to Kelvin by adding 273.15 to degrees Celsius, so T1 is actually 303.15 Kelvin. Our V2 is unknown, and our T2 is 85 degrees Celsius. So remember, you have to convert that to Kelvin. If we do that, we get 358.15 Kelvin. So after we've identified our variables and converted everything to Kelvin, we can set up our equation. So T1, 0.8 liters, V1, 0.8 liters divided by T1, 303.15 Kelvin, equals X liters, or question mark liters, right, V2, over 358.15 Kelvin. If we cross multiply and bring our T2 over to the left, now we get 0.8 liters times 358.15 Kelvin divided by 303.15 Kelvin. Our Kelvin units are going to cancel after I write X liters, right? Kelvin cancels. So now all we have to do is multiply across and divide by 303.15, leaving us with 0.95 liters. And that's it. Okay, let's try this with another practice problem. So in this instance, we have a sample of helium gas, right? The noble gas that, again, we're going to assume behaves ideally, right? And under ideal conditions. So this sample of helium takes up 3.8 liters of space and is held at 35 degrees Celsius and 780 torr, right? A pressure just above normal atmospheric pressure or standard atmospheric pressure. So the two variables that are going to change, again, because we're using Charles' law, V1 over T1 equals V2 over T2. So first, let's plug in some of our variable information, right? We know V1 is 3.8 liters of space. We know T1 is 35 degrees Celsius. Apologies for this loading so slow. And next, we need to identify what V2 or T2 is going to be, right? So we want to determine what the volume of this gas will be at negative 22 degrees Celsius. And again, 780 torr. So we're holding pressure constant. So if we swap out T2 for negative 22 degrees Celsius, right? Remember, you need to convert degrees Celsius into Kelvin. Otherwise, our formulas won't work, right? If we retain that negative in the denominator place or T2 location, that's actually going to mess up our, our calculations when we do them. So be sure to always convert these to Kelvin, right? So our unknown is V2. We want to know what V2 is. So if we cross multiply, right, we bring 251.15 Kelvin over to the left side. We get 3.8 liters times 251.15 Kelvin divided by 308.15 Kelvin. Our Kelvin units cancel. And now when we multiply across and divide, we are going to get X liters, right? Liters are the only units that persist. So when we do this, we should get about right around 3.10 liters. So the volume of space our helium sample takes up under the second set of conditions is 3.1 liters. All right, thank you. If you have any questions, be sure to email me before next class. Otherwise, I will see you next class.